Boy, I sure love making physics videos.
But we aren't very creative, are we?
Nope.
Want to make a physics video?
Yes.
Uncreative like?
Yes, I do. Let's go. So off screen here we have golf club that swings down and hits tennis ball that then connects with a lacrosse ball. Wow, that was really something. Let's watch it again. Holy crap, hold on to your pants, people.
Alright, at this point in time, I, with my incredibly blazing fast hands, will be doing the math portion of the video. Now, our golf club hangs directly over the tennis ball, about 0.5 centimeters off the ground, and we pull it back to 12 centimeters off the ground. And then we release it to strike our tennis ball, which then in turn strikes our lacrosse ball. We can calculate the potential energy of our golf club head in order to figure out how well our energy is conserved throughout our equation, or our thing. And so potential energy equation is mgh equals PE. Our m is 0.349 kilograms, and our g is 9.81 meters per second squared, times our height of 0.115 meters, being as it's 12 centimeters above the original 0.5 centimeters. So this potential energy equals 0.3933 joules, which is a good amount of energy. And so we can calculate the kinetic energy, or velocity, by setting kinetic energy equal to that, and then multiplying by 2, dividing by the mass, and then taking the square root. So theoretically, we find our club head's velocity be 1.501 meters per second, which we know is baloney, as we experimentally found it as 1.17 meters per second, mostly because we, didn't include friction or any other things within our equations. So we have that, and we're good. And so now we have our club head moving at a velocity of 1.17 meters per second with a mass of 0.349 kilograms, striking a tennis ball with a mass of 46.9698 grams, and hits the ball at 3.35 meters per second. Now, we can find the momentum of our golf club by multiplying its mass and velocity, and so we can do so, 1.17 and 0.349 kilograms, to get 0.408337, and we can do the same for our ball to leave us with a momentum of 0.019. Now, this really is not too close to our hopeful answer, and so we have to assume through a constant of restitution that we did not account for in either the cast iron club head or the tennis ball, but also with the continuation of the club head going through the ball and not stopping. Now, our next little bit of math involves our tennis ball striking our lacrosse ball, and although our tennis ball was moving at a speed of 0.35 meters per second as it left the golf club, it has reached a speed of 0.3175 as it reaches the lacrosse ball due to friction. So our B1 final speed is 0.3175 meters per second, and its mass is 46.69 grams, giving it a momentum of 0.0148. Our speed of our second ball is 0.06096 meters per second, and its mass 136.075 grams, so which gives it a momentum of 0.00829. Now, this is wonderful for us because, according to the internet, a rubber ball has a constant of restitution of 0.6 to 0.8, and the constant of restitution of a tennis ball is usually between 0.8 and 0.9. Now, when you multiply these two together, you get 0.48, which is almost exactly our ratios between our two momentums. So, good, conservation momentum up in here, according to statistics. So, now there's still work being done in this tennis ball as it traveled from golf club to lacrosse ball, starting at 0.35 meters per second and ending at 0.3175. So, what must be working on it? Obviously friction. So over this 0.3048 meters, it slowed down, and we'd like to figure out why. So it started at 0.35 again to find an average of 0.334 meters per second. Now, if you multiply or divide the distance by that average speed, you should end up with the time, and which we get as being 0.913 seconds, as so. So we can use this time to multiply it by the difference in our two velocities to achieve our average deceleration of our ball, which ends up being approximately 0.0356 meters per second squared. So we can plug this number in to our F equals ma equation and find the force of friction over this distance. So 0.046698 times 0.0356 to give us a force of 0.00166 newtons. Now, over these, we know our distance, so we multiply our force times our distance to get the work of friction done between our two balls. And we are very happy to have found this stuff, I guess. Wow, that was really a very boring physics video.
I know, but it was fun though, wasn't it?
Yes, I love doing physics videos, and I wish to do more in the future. Excellent.
Yeah.
This is going to be 6 minutes exactly, so
Physics.
chill out for a couple seconds while we sit here, make little finger guns.
Mm-hmm.
We'll probably just cut to black because I'll have to cut it short.